Okay, so I think without further ado, let's begin. So if you're just joining us, so Mykola Didushenko canceled, and I'm filling up for him. So I will tell you about a recent project. I mean, the project has been going on for a very long time, but it should be completed very soon. So it's some of you know about this, that I was working on it. So the talk is called DAHA, Representations and Branes, right? It's not about elliptic integrable systems per se, but there will be connection with the integrability. But it's a talk about representation theory, geometric aspects of representation theory, and so on. So, but it's very much in line with the topic of the workshop. So my collaborators on this project are Sergey Gukov, Satoshi Nawata, Dupay, and Ingmar Sabieri. So it's sort of mix of physics, math crowd. And part of the goal of the talk is to explain what these pictures mean, right? So when you look at the picture at the bottom left, well, you can sort of try to fantasize what comes to your mind, right? So I don't know what about you. I see the Dynkin diagram for affine D4, right? And that will be part of the construction. And there is some representation of double affine Hecke algebra in this case. Okay, so let's get going. So I want to start really easy. So in fact, I'm recycling a talk that I gave yesterday at Louisiana State University at math department. So sort of it was intended to be a broader audience, but I think it would be good since it's morning. We can start pretty slow. And yeah, so ask questions at any time whenever you have them. So the modern quantum mechanics is, well, the quantum mechanics in 21st century is a modern symplectic geometry. So we can, unlike quantum field theory and quantum mechanics, we can have everything put on a very robust footing using methods of modern symplectic geometry. So let me give you an example. Right, so consider a harmonic oscillator. So classically, it's Hamiltonian, or total energy is the sum of kinetic energy and potential energy. So I scaled all the dimensional constants to 1, right? And then here's the graph of the potential. So the particle in this quadratic potential would go up and down, right? So when it's up, then the potential energy is maximum, kinetic energy is 0. And as it goes down, the kinetic energy increases and potential energy decreases. So these two components, they kind of balance each other out, making sure that the total energy is constant, right? So geometrically, we can illustrate this fact by drawing the circle in the phase space, right? So if you draw in XP plane, right, in these coordinates, it will be a circle, right? And the space is a symplectic manifold, in this case two-dimensional, with symplectic form dp dx. And the energy condition will be the equation for the circle with the radius e, where e is the total energy. Then there's a disk, and then there's a boundary of the disk, right? And this boundary is in fact a Lagrangian submanifold, right? So what is the Lagrangian submanifold? It's a middle dimensional submanifold, right? Such that the restriction of the symplectic form on that submanifold vanishes. Well, in this example, it's pretty trivial that it vanishes because it's sort of too low of dimension, but you can of course imagine that I'm talking about a system of several coupled oscillators, right? And in that case, the dimension of the phase space will be twice the number of degrees of freedom, and the Lagrangian's dimensions will be half of that. So then a symplectic form is locally exact on this Lagrangian, and we can take its primitive, and this is called, of course, the Liouville form, right? Which you can write as p dx. Okay. Is there a question?
Wait, but it's 0, right? On the Lagrangian. It's not just locally exact.
No. Omega is 0. Del inverse, the inverse omega is not 0.
Okay.
So you PDX is not 0 on the Lagrangian, right?
Okay.
You integrate PDX, so action is the integral over the path of PDX. Yeah. So
okay.
Yeah, in fact, yeah, so that's what Yegor is asking. So yeah, so like there, okay, I'm coming to that. Other questions? Okay, now let's quantize things, right? So let's talk about quantization. So we'll know the standard answer from the textbooks. I just want to illustrate this using symplectic geometry. So the quantum oscillator is, assuming the frequency of oscillations is 1, as it was here, right? So then the energy levels are n plus 1/2 multiplied by the Planck's constant. And then, so they're equidistant from each other, and then there's a zero energy shift, which is h bar over 2, which is, of course, very important. And then sort of geometric way to express this fact is that we can, so there are two ways. So either we integrate the symplectic form, the Liouville form over the Lagrangian, right? Or we calculate the symplectic volume of the disk, right? So we would integrate the symplectic form dp dx over the disk. And then the quantization condition would tell us that the symplectic area in units of Planck's constant is integer, well, up to this 1/2 shift. It tells us that out of all, so of course you can draw, classically in phase space, you can draw circles and disks of any radius, right? But it turns out that the quantization condition selects only those radii for which this is true, for which this area is an integer. And so that's an example of a quantization condition. And it also shows you that not every Lagrangian classically survives quantization, right? So only circles of certain radii. Let's say a couple of more words about the story. So we have coordinates and momentum, right? And upon quantization, they become quantum operators that would act on certain Hilbert space. And then we have a symplectic form, omega, and then with which there's an associated Poisson bracket, and that Poisson bracket is upgraded to the commutator. So in this example, operators P and X form so-called Heisenberg algebra. So the P and X commute to, which is the standard convention, negative I times h bar. And sort of, if you write it in terms of some coordinates on, say, function of coordinates, so X operator X with multiplication and P operator X with the derivative. And then the Lagrangian constraint, right, the equation for the circle in phase space is now replaced by the quantum operator. So basically you put hats on everything. Of course, if it's something more complicated, you have to worry about normal ordering and stuff like this, but I'm not going to go into this. And then it now acts on a state on this function z of x, which will be the wave function for the quantum mechanical system, or state in the corresponding Hilbert space. And here, the quantization condition, which I mentioned on the previous slide, will be manifested as follows. So this is a second order ODE, right? So P squared is basically negative h bar f double prime, right? So plus potential, and then the square, if require the boundary conditions at infinity, so that the solutions will be square integrable, that would disallow all values of E, but this discrete set, right? So for example, for n is equal to 0, we'll get this famous Gaussian. So Z would behave like this orange curve at the bottom. Okay, so that was the kind of reminder, which I'm sure everybody knew. But I wanted to illustrate a couple of facts here, which will be important in general for sort of the whole quantization program. So geometrically, we say about the following, right? So we start off with the symplectic manifold, M with symplectic form omega, so that the whole manifold is promoted to the Hilbert space. Then algebra of functions on M on that space becomes algebra of operators and on the Hilbert space, and they act on it. And then there's some more sort of finer details, which will be important for my talk, is that the Lagrangian submanifold folds, they become states in that Hilbert space, right? So for instance, if the Lagrangian is described by a system of polynomial equations, like it was the case with the oscillator, so you can think of some complete intersection or stuff like that. that becomes well, this equation. So now f hat acting on z equals to 0, and then you need to solve this difference or differential equation. In my case, it will be difference equation, and you find the corresponding state of the Hilbert space. Yeah, basically, you'll find the spectrum. I mean, it's like, it's a not stationary Schrodinger equation, but written as that something acting on z is equal to 0. Okay. So to find further connections with what about to follow in the main part of the talk is that so I'll be talking about instead of Heisenberg algebra, which is the case in oscillator, I'll be talking about a more complicated algebra, which is called DAHA, double affine Hecke algebra. It's a very interesting beast, and I hope you like it as well if you haven't seen it before. So the algebra of operators, which arises from quantization, will be exactly that algebra here. So I kind of was preparing this to be as a math talk. So if I have a sort of string theory realization of this, you can ask me later. But yeah, basically we'll describe the algebra of operators here, and then the representations, its modules of DAHA, its representations will form the Hilbert space, right? And then so in more detail, those states which come from quantization of certain Lagrangians will be highest weight vectors of DAHA, and we'll be able to sort of describe them very explicitly. So instead of differential equation like Schrodinger equation for the oscillator, I will have the difference equation. So Y will be essentially Macdonald operator, right? So everybody here should be familiar with that. So so like a Macdonald-Ruijsenaars integrable system will be a part of DAHA. So it's an interesting story there. And then the Z, for example, here is shown as to be the highest weight vector of Y, a Macdonald Y minus some complex value. And then the duality that I'll be sort of describing is that the certain very nice symplectic manifold M will have some Lagrangian submanifolds, which would look like this, and even more bizarre than this. And their symplectic volumes, so obtained by integration over the symplectic form, will compute dimensions of some representations, which will identify independently on the other on algebraic side. Okay, questions? I hope so far it's all pretty clear. Okay, let's begin. Now, a little bit of history. So DAHA, double affine Hecke algebra, and related algebras, which are obtained by certain limits when we degenerate some parameters, they introduced by Ivan Cherednik, and he wrote a book about it, which is here it's a very nice textbook. So he introduced them in the study of Macdonald polynomials. So yes, like he wanted to prove Macdonald conjectures using his formalism, which he successfully did, and he developed this, came up with this idea of this new algebra, which sort of combines many other structures in representation theory. Then Alexei Oblomkov demonstrated that in type A, DAHA is what is called deformation quantization. So it's a one-parameter deformation of Poisson structure on the Kaloger-Moser space. So that will be the symplectic manifold M that I mentioned on the previous slide. So in my story, I'll be working with SL2C, sort of Kaloger-Moser space for 1 degree of freedom for one particle, and it will be described as the moduli space of SL2C flat connections or SL2C character variety of a torus with a puncture, right? And then using this geometric approach, we'll and this quantization list, right? Will provide geometric construction of DAHA representations.
Peter?
Yes.
What do you assign for the monodromy at the puncture?
Just the number. Like when it's a diagonal matrix with one eigenvalue.
Okay.
It's when it's just
generic.
SL2.
Generic semi-simple. Generic semi-simple element.
I mean, but I mean, it's SL2, right? There's only one thing you can put there.
Sure. So, I just.
Yeah, I mean, there's a high rank generalization, which is not done at all. It's very complicated. So there you can ask, what else can you put on the puncture? Other questions? Yeah, just maybe one more comment before I go with details on DAHA is that sort of this list, right? So it says art of quantization, right? So it's really more like a wish list, right? So as mathematicians, right, or physicists, we don't have like a universal recipe of how to quantize things, right? So as I will show you, and I hope I showed you when I talked about oscillator. So for example, not every Lagrangian manifold is quantized, right? It was pretty obvious with oscillator, but you can imagine it will persist later, right? So for example, here, basically we'll be comparing conditions on those Lagrangians with certain shortening conditions on DAHA representations, and yeah, so those will be very strict, very explicit constraints, which are not guaranteed to be satisfied. So you may be, you must say, okay, let me pick some symplectic manifold, right, and it may not be quantizable in a way that we know, right? So there are several adjectives people add to word quantization: deformation quantization, geometric quantization, and I will be using even upgrade of that, which is called brain quantization by Branes. And yeah, so none of those are actual quantization, right? So in actual quantization, h bar is a number, right? So the reason why your cell phones and stuff work is because h bar is a number, right? Not because it's a formal parameter. And in all those sort of mathematical approaches to quantization, h bar is a formal parameter, right? So you are not allowed to substitute to it its value, whatever it is. Right? Okay, good. Let's begin. Are there any other questions? Okay, so let me describe a couple of alternative constructions of DAHA, and then like if you read the paper on DAHA, usually authors just put a page-long definition. I'm not going to do that, so we'll do it step by step. So let's say G will be the Lie algebra, which will be in my case SL2. And then so first we introduce the Hecke algebra, or Iwahori-Hecke, which is a deformation of the group algebra of the while group of G. Right. So I'm not going to give you the full definition, but basically let's just look at an example. So say for SL2 we have so while group is Z2. Right, so its group algebra is generated by relation t squared equals 1. So t squared can be 1 or minus 1, and then if in this case it's a one parameter deformation with this parameter t, and there's one generator, and the relation is capital T minus little t times capital T plus t inverse is equal to 0. Right, so one generator, one relation for SL2. So this is Iwahori-Hecke algebra. And you can sort of imagine how this generalizes to higher rank. Then affine Hecke algebra, or AHA, for SL2 is the following quotient. So we take polynomial, we have polynomials in this new variable x and x inverse and t, right? So x will be the affine generator and mod out by two relations. So there's a typo here. So the one that we see before over here in Hecke algebra, and this relation which looks like txt equals x inverse. So we sort of did the affinization, and then finally, finally DAHA is two copies of AHA, right? So there's AHA generated by x and t and by y and t in the presence of additional relation, and parameter q also takes values in C star, and this is it, right? So we have field of fractions, so rational functions of q and t, tensored with a polynomial ring of x inverse y, y inverse t, and then there's a AHA relation for x, for y. This is the stuff we see before from Hecke, and there is a this quadratic relation that binds together x and y.
Why in your AHA above you didn't have something telling you about t plus or minus, little t plus or minus, as you do with?
Oh yeah, I'm sorry. Yeah, you should also put, I should put that. Yeah, absolutely. Yeah, that's right. So you should put C of braces t plus minus 1. Yes.
Great.
Yeah, it is there. Thank you. Good point. Other comments, questions? Now, geometrically, we can think of it as follows. So start off with the torus without the puncture, right? So there's just would take one point out, right? Mod out by Z2, which is the Weil group of SL2, right? And then we'll look at the fundamental group relation for this surface, right? So here it's, the pictures are drawn on a double cover. So think of the square as the fundamental region of the torus, and this is the puncture, right? And then sort of T will be like half of a monodrome around the puncture, and X and Y will be something like half longitude and half meridian cycles of the torus. So you can kind of color by color, you can see that the meaning of each of the relations here. So we're gonna put TXT equals X inverse. It's the same as you basically go, you do T first, then you do X, then you do T again, right? And then it's as if you go, it's the same as you need to go backwards, and same thing with others. So here, this relation here, Y inverse, X inverse, YX is the same as T negative squared, right? So holonomy around the, but yes, so there are two different ways, equivalent ways to express the holonomy around the puncture. Okay, and then yeah, so the okay so good. So if this is 1, right, it's called yeah, right. So if this is 1, then this is just the fundamental group relation. So there is no Q here, right? And then the deformation, or like rather, sorry, central extension of this, which is called elliptic braid group, is obtained by this orbifold fundamental group of the torus, modded out by the relation which contains Q. And so that's elliptic braid group. And the from this approach, full DAHA is written like this. So CQT is this field of fractions. I simplified the notation a bit, times this, and divided by the same relations that we saw on the previous slide. So there is a notion of the torus with the puncture here, which we'll exploit later. Okay. Now there is a big zoo of symmetries here, which will be again important. So there's a discrete symmetry Z2 cross Z2, which acts on generators in an obvious way. So it will have, it will later be, yeah, so we call them Xi1 and Xi2. This is how they act. And then there is also mapping class group of the torus, which I wrote slightly in unconventional coordinates. So here, for example, tau plus is this matrix. It's not standard S and T generators; they're slightly different. And tau minus is the lower diagonal one. And additionally, there's also this nonlinear involution iota, which inverts the parameter T. Now, then you can see here Z2 cross Z2 is also the outer automorphism group of Dynkin diagram for affine D4, and that of course will be manifested very soon. Now. Even that, what I showed you looks pretty complicated, right? So we would like to make things simpler a little bit, and we'll symmetrize all the polynomial expressions in X and Y. So instead of a full DAHA, we'll consider spherical subalgebra. So this spherical DAHA is, we can show that this element E is idempotent, right? So it squares to itself. And the spherical subalgebra is just the whole DAHA, which is sort of sandwiched between these two elements. And then everything will now depend on symmetric polynomials of X and Y. Right, so little x, little y, and little z, which is the combination like that. So then the relations from the previous slide can be sort of succinctly rewritten in a kind of in this form. So you have so X and Y Q commutator, whose definition is given over here, is equal to Z with this prefactor Q minus Q inverse. And then 3 other relations are obtained by just cyclic permutation. And also there's a cubic relation here. So there's X, Y, Z plus some quadratic expression equals this number, which also, well, it's, which also appears. So now the semi-classical limit will corresponds to taking little q to 1, right? And then we'll have, so which sort of shows you that the, yeah, so this DAHA, spherical DAHA becomes this algebra functions on that space, on the modular space of flat connections on the puncture tors with a structure group SL2C, right? And it's given by that space is described by this equation. So I'll show it to you in more detail on the next slide. So there's a cubic in X, Y, and Z in C3, who is given a bit this equation: x squared plus y squared plus z squared minus x, y, z minus 2 equal t squared plus t minus 2. Don't worry about the tilde. There's just some rescaling normalization. So yeah, so the geometry behind DAHA is this SL2 character variety, the modular space of flat connections in SL2. So consider fundamental group of the torus, right? It has 3 generators in one relation. So meridian, longitude, and the C, which is puncture around which is the monodrome around the puncture. That's what Sabyok was asking. Consider some representation of the consider SL2 representation of this fundamental group. And then you can denote X to be trace of M, Y trace of L, and Z trace of ML inverse. And sort of it's a 5-minute exercise to check that equation is described by this cubic here. This is a projective cubic, it's also called Markov cubic. And it's geometrically, it can be understood as the elliptic fibration of Kadaira type I0 star. So it's there's a one-dimensional base and then one-dimensional fiber, and the generic fiber is an elliptic curve, which at the origin, right, over the fiber over the origin on the base is singular, and its singularities of this type I0 star. Okay. So this is the theorem by Oblomkov, which we'll be using. So DAHA is a deformation quantization, right? So sort of what this slide and the previous slide illustrates, of the coordinate ring of the moduli space of SL2 flat connections, which I will be calling X for short in the following, in the present of the, excuse me, with respect to Poisson structure omega j, which is given by this formula here. So if little f is the left-hand side of this equation, right? So then you can write the symplectic form like this. It's dx wedge dy divided by df over dz. And sort of you can show that it's invariant with respect to the symmetries that I showed you a couple of slides ago, right? So it would, clearly there's a symmetry between x and y and z. You can replace them by cycle. And yeah, so you'll get the you'll get this expression. Now, what I'm going to do with the rest of the talk is we'll do 2 things. We'll study first representations of the spherical DAHA. So they'll describe category of representations. So objects will be representations, and morphisms will be equivariant maps between those modules. And on the geometric side, we'll look at Lagrangian submanifolds of X, right? Which are, well, we'll have some explicit geometric realization, and then we'll study the conditions upon which those manifolds are can be quantizable, and we'll relate those to the representations above. So the dimensions of DAHA modules will be equal to symplectic volumes of those Lagrangians. And these Lagrangians or Lagrangian branes, they form Fukaya category of X with respect to certain symplectic form, which I'll specify in a couple of slides. And yeah, so basically the theorem that we're proving that for SL2, there's a equivalence in some derived sense between the representation category of DAHA and Fukaya category of X. Any questions at this point?
Yeah, Peter, where are T and Q hidden, or have they just disappeared?
Ah, good, excellent. No, so they do not disappear. So yeah, indeed. So T in the there's T in the equation. Yeah, so T will be some volume parameter, if you like. So as you change T, certain symplectic volumes will change, right? Now Q is not in the classical equation form for the curve for this space, but it will appear in a quantization. So in DAHA, of course, there is Q, right? So Q will appear literally like in the constructions of the representations, there will be Q and T, and there will be some relationship between them. In geometric side, there is no Q a priori, but it will appear as we impose the quantization condition.
Thank you.
Sure.
Well, so when you talk about the Lagrangian of manifolds, it's holomorphic Lagrangian, right?
Yes. So
And
it will be a hyperkähler space, and then depending on how you look at this, it will be the holomorphic and say I complex structure J, or some linear combination of the two. So yeah.
oh, it's not omega J holomorphic symplectic, holomorphic Lagrangian.
So that as you turn on this deformation or B field, it will change. It will turn.
Okay,
So like,
okay.
yeah. So if with no B field, it is. But if basically you'll see. So like there'll be the whole family of branes which are parameterized by complex phase of the Planck's constant.
Maybe this is related. So what is a small omega x?
I'll write it down. Yeah, basically it will be omega, I think, I plus I omega k, something like that. Yeah.
Okay.
Good. Okay, let's proceed. So yeah, and then yeah, we'll talk about brane generalization, although like probably not too much, but due to the time constraints, just wanted to illustrate the idea. Okay, now for those of you who like integrable systems and explicit formulas, so here is the so yeah, but what is DAHA? So DAHA, so think of it as a Macdonald operator, Y. So here omega is the shift operator, so just X by Q multiplication, right? And yeah, so there are two others, right? So there's little x and little z, and we discussed how they commute with each other. So think of Macdonald operator like as a center, right? And then x and z are something else. So we'll be discussing polynomial representations of the thing. So when eigenfunctions of y will be polynomials, but in fact you don't have to. So you can just formally ask yourself, what happens if you take just formally write down this difference equation, yz equals some complex constant times z. So I wrote it in this form because we know that the y is a symmetric operator, and just ask what are the possible values that z can take, right? Which class of functions are we talking about? And you can just formally find that z in fact is a series, right? So unless you specify certain values for a, z will be a hypergeometric series. It's a this is a 251 hypergeometric function, right? Which is infinite, right? And it appears in many other applications, for instance, in enumerative algebraic geometry and others. So I talked about this in various papers I wrote with Anton Zeitlin over the years, and that was sort of part of this program that we've been working with connects geometric representation theory, integrable systems, enumerative geometry. Yeah, so my talk is not going to be about this. But anyhow, yeah, so in general, Z is a series, and in this case, we're talking about some infinite dimensional representations of DAHA. But then if you impose this condition that A is a discrete value, so it's Q times J to the power of J times T, then we'll get Macdonald polynomials of type A1. They're labeled by spin J half representation. And here they are. So, yes, so basically it's the fact that, yes, if you substitute A to be this value, the series will truncate and you'll actually get a polynomial of degree J. Some examples here. So P1 is just this, P2 is this one, and so on. So I think this normalization is slightly different from Ian Macdonald's book, but it doesn't matter. Okay, now how do we describe this representation in more detail? So the so it's in fact you can show, I mean, it's kind of obvious that the ring the polynomials, the Macdonald polynomials, they generate the whole ring, right, over this over C of Q plus minus 1 T plus minus 1, and you can describe it this way, so that we'll make two linear combinations out of little x and little z, and call them raising operator and lowering operator, right? So they differ only by one little constant here, so it's basically Q So like in the previous slide, so this was A, right? And this was A inverse. So if we have these two different linear combinations, we can show that what they do is that if we act on this with the raising operator on Pj, you go to Pj plus 1. So it's a raising operator. You could go to the next next polynomial, and then if you go act with L on Pj, you go to Pj minus 1 with some interesting rational coefficients in front of them. Yeah, and y, and they're all eigenvalues of y, right? So they are, yeah. So they're all highest vectors of y. So for general values of q and t, this is what you have, right? You start off with 1, and then you raise it. You get p1, x plus x inverse, p2, p3, etc., etc.
So the eigenvalues of y are increased by q, right? Q to the j.
I mean, like the eigenvalue answers. I mean, so each of p's eigenvalues are eigenfunctions of y, right?
Right. So, and the eigenvalue was a to the jt.
The eigenvalue was
q to the gt.
Yes, a plus a inverse, where a is equal to q to the jt.
Thanks.
Yeah. Good. Yeah, and then sort of now what may happen is that as you look at the so this expression here, right? So which appears in the yes, basically see there's this polynomial here which can vanish, but it also appears in the denominator. So you don't want this to vanish, right? Otherwise you're going to have you have a problem with action of L. So instead you need to look at other ways when polynomial, when this action can vanish. So what may happen is that you act with a lowering operator on some pj, and then you get 0, right? So and you can see from the shape of the rational function that it shows over there that it happened in 3 different cases. When q to the 2n is equal to 1, when t squared is negative q to the negative k, where k is an integer, and when t squared is q with a plus to the negative negative odd integer. Like, so those will be all 3 different cases which we'll have to explore. And then when this happens is that you act with a 0, so the representation truncates, and then you have this short exact sequence. So if V is the whole infinite module, you get a submodule S, which is also infinite, right? And you get the factor V mod S, which in this case is finite dimensional, of dimension J, right? So there are exactly J polynomials over here, and that's what we're trying to understand. Okay, now let's talk about geometry a bit. So we'll talk about representation theory. Now let's talk about geometry. We'll describe geometry of X, of the modular space of flat connections, using so-called non-abelian Hodge correspondence. So it relates, in general, representations of the fundamental group of smooth projective algebraic varieties with Higgs bundles, E and phi, right? So you have so the right-hand side is called Hitchin moduli space, and it's so it has this Higgs bundles, and each Higgs bundle for SU2. So here it's SU2, right? We have it's a holomorphic vector bundle over CP, which is punctured torus, with homomorphic section or Higgs field of canonical tensor with adjoint, a tensor with OP, and sections of OP are functions, meromorphic functions that have poles at the origin, right? So otherwise they are holomorphic. So the connection A of this bundle, right? It has this prescribed singularity behavior at the origin. So theta is the radial angle, around, in the trivialization around the origin, and phi has these 2 parameters, alpha, beta and gamma, and A is equal to alpha times d theta. So the way correspondence works is that the moduli space of solutions of the Hitchin equations here, right? So you can write down those equations, is translated directly to the flatness condition for this connection curly A, which is equal to A plus I phi plus phi bar. So there's a complexified combination of the connection and the Higgs field, which is the complex connection, and that will be the SL2 flat connection on the in the character variety. So MH is a hyperkähler space. It has three, well, you can write three different complex structures: omega I, omega J, and omega K. Right here is the standard formula for it. So delta is the co-derivation, and then we can write down also the triplet of holomorphic symplectic forms. This big omega I, big omega J, and big omega K, which are the following linear combinations of these three. So what effectively happens is that we are kind of complexifying everything, right? So all those omegas are complex by themselves, but then sort of as if we are going into quaternionic sort of notation. So we're going having even more forms, right? So for example, omega J here, the one that we'll be looking at when deformation in geometric quantization, has information about complex structure K and complex structure I. And then the geometry of the sort of deformation space of this manifold will be described by the triplet of parameters alpha, beta, and gamma, which describe the singularity. And then depending on which complex structure you look at, the meaning of these parameters will differ, right? So for example, Kähler modulus will be alpha, beta, gamma for I, J, K respectively, and corresponding linear combination of complex moduli, complex deformation parameters.
Beta, alpha, beta, gamma are complex?
Yes. Yeah. And they are complex by themselves, and yet I'm sort of making the complex thinking.
That's fine.
Yeah. Yes. Okay. So I think it's more or less just another. I can probably skip that. Yeah. Basically, might be valid. So so this is the space, right? And then the symplectic form Kähler form. So for example, when t is equal to 1, this x, the m flat is this factor. So it's c star cross c star mod z2, whose real slice, kind of the skeleton, looks like a torus mod z2, right? So it's basically, it has a sort of four singularities. This is so-called Pillowcase. Now so let's describe the Hitchin fibration in more detail. So we have the projection from MH to the base, to the Hitchin base, and it's an integrable system, right? It's a Hitchin integrable system, right? So its fibers are abelian varieties, Liouville tori, and it sends the tuple E and phi, right, bundle, and the Higgs field into trace phi squared, right? So the way it's constructed, they're holomorphic in complex structure I. So this is how it looks like. In the only, so as I said earlier, the fiber of a generic point on the base is an elliptic curve, right? It's T2, and then the only singular fiber is the preimage of 0 under this projection, which we call N, or a global nilpotent cone. And sort of, it looks like the topology of this is 5 CP1s, which are connected like this at 4 different points. So it's a So that's what kind of that's how this Kadaira I0 star type fiber bundle looks like. So when all of those alpha, beta, gamma vanish, right? So then we get the Pillowcase. So this V here, which is sometimes called the Bun-G component, which appeared in Pavel Letningov's talk yesterday, in slightly different context, is this component over here. And then when this happens, that this divisors D1 through D4, they shrunk to 4 points, right? So they are not there. And then as we go away from the beta equals 0 locus, and basically away from this locus, a lot of things will change, right? So we'll have the complex structure in which everything is holomorphic will also change. Like, not only you change the sizes of each of those components, but also like the holomorphic and Kähler structure of the whole fibration will also change. So holomorphic Lagrangians with respect to omega I, which happens here, sort of in physics literature, they're called branes of type BAA, right? So holomorphic in B, Lagrangian in A, in J, and Lagrangian in K. but that can change. Okay, so we have
is your base, Peter, actually P1?
yes.
Thanks.
Yeah. Now the sort of right. So the intersection form of this fiber is the intersection form here is the Dynkin diagram for a fine deform, and it has one null vector. So yeah, if you take this combination of 5 components in the homology, this vector will be annihilated by the intersection form, and it corresponds to the torus, right, which we expect to have a trivial class. Right? So kind of you can kind of think about this way. So at a generic point there's a torus, and then as you sort of as it approaches the singularity, the origin, it kind of something strange happens to it, right? So it breaks down into those components, and yeah, we'll talk about this in a moment. I'm actually going pretty slow, but yeah, so should just show you some examples now. So for generic value, yeah, let's talk about the deformation parameters a bit more. So then for generic values of beta and gamma, so if you turn on beta and gamma, the embeddings of those cycles di and v into mh are no longer homomorphic with respect to I, right? And now you'll have a different type of vibration. So now I0 star will split into 3 singular fibers of type I2, right? You can kind of show it, sort of make sure that this is true by looking at the sort of parameterization where the singularity is at infinity. So yes, this is the elliptic curve, and then you'll see that there will be 3 points in a base b sub little b sub I, right, which are given by these expressions over which the fiber looks like a torus, which is pinched in 2 points, right? So there are 2 double, now it's sort of split into 2 CP1s, and then they have 2 double points over here. Then you can expand it in a homology basis of what happened before. Okay, now, so yeah, what we want to do, we want to compute some symplectic volumes. Yeah, so I'll kind of yeah, let me just I'm going to show you some formula here. So then in this Pillowcase frame, we have yeah, so you can compute integrals of omega I, omega j, and omega k. They will be expressed directly through those alpha, beta, and gamma, and do the same for the generic Hitchin fiber when f is the elliptic curve, and for all this di's, which you call exceptional divisors. So it all can be done. There's the symmetries acting over here. And this is the crown jewel of sort of quantization story. It's called canonical quasi-tropic brane. So it's a line bundle over X over the whole space, right? Whose first Chern class is equal to the whose first Chern class will be related to the symplectic form omega, which in this case is the imaginary part of omega j, the big omega j, which is the combination of the two, divided by the Planck's constant, right? And then this Planck's constant will be related to parameter q in DAHA as an exponential. So q is an exponential of the Planck's constant. Here it's e to the 2 pi I h bar, and h bar itself is complex. So as we change the phase of h bar, right? So the particular linear combination of original symplectic forms, omega I and omega k, will change with this phase. So to make a long story short, so we impose the condition on this omega x. So yeah, so omega x is the imaginary part here, and then we say that the curvature of this bundle, right? So this is called a brane. So it's a certain flat unitary bundle over the Lagrangian manifold with respect to omega x, and the BCC brane is a line bundle over the whole x, over the whole space, right? And then the additional B field source, which we turn on, sort of it's an additional ingredient, plus the curvature is not equal to 0, so it's not flat, but rather it's equal to this new symplectic form times the complex structure J. Yes.
How does tuning H bar relate to? How is it related to turning on this B field here?
You disappeared, probably mute button.
I'm sorry. So you're tuning this phase of H bar or the Q.
Oh, okay. So if you're familiar with Gukov-Witten coordinates, so they have, there's alpha, beta, gamma, and then also eta, right? So B would correspond to eta. I'm not talking about this here. So there's some additional constructions. Like there's also eta P that you can turn on. So so basically you need to turn it on to for consistency. Yeah, like I mean it's a sort of it's an indispensable part of the formation of the quantization by Branes story. Like yeah, so basically yeah, so F plus B is the real part of omega, and then omega X will be the imaginary part of omega. Yeah, so like it's not clear from here, but yeah, basically B will change. Like it will affect this formula.
So in the spherical DAHA, we consider non-unity value of Q, and that corresponds to turning on B field. That's what you're saying? Yeah,
I think so. In one of the cases, yeah. No. Like we'll ask me this later if I want to show you the formula for the nth root of unity for Q.
But can I ask you one more? But so in the Q to 1 limit, we have the notion of the Lagrangian submanifold as a definite submanifold.
Yeah.
By turning on non-unity Q, what does it mean to have Lagrangian submanifold in the spherical DAHA language?
So you're saying say have Q to the n equals 1. Okay, so when Q is not equal to, I mean like there's no continuous limit as Q goes to 1. That's what you're saying.
Yeah, I think I'm asking just a simple question. In Q goes to 1 limit, we recover the coordinate ring of the
that's right.
functions, and that from that we can just consider holomorphic Lagrange as a manifold, which is holomorphic Lagrange with respect to omega j. But now you're turning on non-unity Q, right?
Yeah, so then it will be holomorphic with respect to some combination, not omega j, but omega j plus.
Right. So what does it mean to have holomorphic Lagrange as a manifold in the language?
Well, I mean, in hyperkähler space you can rotate things around, right? It just becomes holomorphic. It's not BA anymore, right? It's something else.
I can't imagine that, but I'm asking at the level of the algebra, what does it mean? Okay, but
no, it means that quantization goes in that complex structure. That's it. And so
I see.
Yeah. So yeah, so I don't have to say I don't have to do it every time with omega j. So yeah, so the symplectic form will also change with the B field. Okay, so now so basically because BCC brane is a bundle over the whole X, so the space of BCC strings or space of endomorphism of this bundle is associated with the algebra itself. So this space of Hom BCC parameterized by H bar, as shown before, it provides the deformation in a space of holomorphic functions on S, which will be the algebra itself. So Hom BCC is DAHA, spherical DAHA, and then the space of representations Hom BCC B prime, right, where B prime is Lagrangian, right? It will correspond to representations, right? And then because we can, as shown in this picture, we can combine strings, so we can have BCC string can be combined with a BCC B prime string, right? Then it provides you the natural action on the space of on the space over here. So in other words, the deformation so brane quantization of X gives you the algebra, right? And quantization of Lagrangians provide you the representation. Yeah. So let me show you some examples. So the Lagrangian branes are defined in a standard way. So there's a Lagrangian, basically there's a bundle over L. L here is a Lagrangian, and it's twisted by the canonical, by the square root of canonical bundle, KL -1/2. And that's it's like ingredient of the quantization of geometric quantization. So first you have what is known as pre-quantum light bundle, and then you need to twist it by the square root of the canonical bundle. You would impose Lagrangian flatness condition like that. So those branes are flat. as opposed to BCC brane, which is not. And then the dimension of the corresponding representation is obtained by calculating the dimension of the space of sections. So the dimensions of the zero cohomology in coefficients with the BCC tensor BL inverse, and that can be calculated using Grotten-Dick-Riemann-Roch formula. So in this particular example, it's literally when the Todd class is equal to a roof genus times this Chern class of canonical. There are some cancellations. So the dimension of the space of strings, so dimension of space of BCC B prime BL strings, is just given by integral over B field over the F plus B over that Lagrangian, right? So, and this is this will be exactly the symplectic form that we will be integrating over. So and so Lagrangian branes will be objects in Fukaya category. So now let me show you some examples before we, because I'm running out of time. So a generic fiber, so the F, the elliptic curve F, which is sort of away from the singularity in the Hitchin fiber, when theta is equal to 0, so Planck's constant is real, then omega script x is equal to negative omega k divided by h bar, and the Lagrangian, and then the sort of condition on the brane is f plus b is equal to omega I over h bar, and then you can calculate here that this dimension of space of BCC BF strings is equal to integral over this elliptic curve of omega divided by h bar, omega I divided by h bar, which is just 1 over h bar. And we need to impose quantization condition, which says that h bar is equal to 1 over integer, which is always the case when we quantize compact manifolds. And if you look at the table from the representation theory data, the shortening condition will be this, that q is equal to e to the, so remember that q is e to the IH bar. So if you have q equal to the 2 pi I over m, it shows that this is a primitive root of unity, right? And that corresponds in DAHA language to a certain finite dimensional representation, which is called FM, with some additional data, which I don't want to go over. And then you can do the same. You can do the same for other types of Lagrangians. So the singular fiber of type I2, you would compute the symplectic volume of that Lagrangian submanifold according to our prescription. You're going to get 1 over 2 h bar. And in this case, it corresponds to this polynomial representation P, which we call UN, a script UN1, which is the factor of the whole module over Pn, which is given by this polynomial, and so on. So you can calculate symplectic volumes of all Lagrangians and compare them against the dimensions of the corresponding representations. And there is a one-to-one correspondence between all of them. So there's a table which relates finite dimensional representations of DAHA, which is obtained. Basically, you can open Triadnik's book and just find them all here. Although we were able to find one more representation, which is not in his book. Match them against these conditions on Q and T. So there are two distinct conditions on the root of unity. One is for every m, and one is for root of unity, and one for even root of unity. Like this, and then the here in this table, in the last column, we talk about we list the conditions on the Lagrangian branes for which these Lagrangians exist and they can be quantized. Yeah. Okay. So since I'm running out of time, let me just show you the final statement. So the main theorem is that so let's see P be the punctured genus 1 Riemann surface, and X is the moduli space of flat connections of SL2 with the prescribed monoderm at the puncture, and then the spherical double affine Heike algebra, and this is the spherical double affine Heike algebra of type A1, and then there is a derived equivalence. Well, there's a very interesting story about derived categories between the Fukaya category of X and the category of finite dimensional modules, which in fact forms a subcategory in a larger category of all representations. And then Fukaya category is a subcategory of so-called category of A branes, which includes also this BCC brane. Okay, good. So sorry for running out of time. I stop here. see if you guys have any questions.
So how does one understand this from the point of view of something like AGT or this kind of story?
Well,
so this modular space of flat connections is.
Yeah. So sort of the AGT connection would be this: is that the where's my picture with the bundle, right? So the so you know that there's an enhancement, right? In rank 1, right? There's an enhancement to SO8, right? So if you say you look at a class S theory, what is it, of type because sphere with 4 punctures, right?
Right.
Now, well, so here in rank 1, so there's a accidental equivalence between the modular space of this curve and this curve, right? And you can talk. So I talked about the torus, but you can talk about sphere with 4 punctures. And basically, formula will look the same as a mine. You just say different words, right? So here it's kind of here. So here, say you have 4 singularities of type A1, and sort of part of the geometry that I described is when all singularities they come to one singularity, and it become this instead of A1, you get this I0 star, right? Which somewhat reflect, I think, can be attributed to this enhancement of the global symmetry in infrared to SO8, right? But here it's even bigger. It's not just SO8. SO8 is just only this, only 3 components. Here it's even affine SO8. Yeah, so there's some remnant of Guyota curve, like this AGT story there. But like we're not focusing on, like we already, so yeah, you can talk about gauge theory, which stands behind this, right? It's either QCD and F equals 4 and C equals 2, or it's the N equals 2 star theory, right? For the torus, the parameter T here is related to in this 2 star case, parameter T is related to the mass, right? To the N equals 2 star mass. Yeah, so this is all standard, right?
Maybe, so we can think of this N equals 2 star theory, and the conformal block is the one point block on the torus, right? And the Valin-de-Leeuw operators acting on this conformal block, and that gives you this spherical DAHA. In the Macdonald-Ruijsenaars limit, we recover the coordinate ring of the.
Oh yeah, actually, it's okay. Good. Right. Yeah, I should have said that. Yes, so kind of a fit interpretation, right? So you have Wilson lines and Tooth vortex lines.
Yeah, precisely.
Yeah, good. Yeah, thank you. Right. So and then so from this point of view, DAHA is exactly algebra of these line operators.
Yes.
Right. So or K theory, right? So it's a K theory of these line operators.
And I think your shortening condition will impose conditions among the equivariant parameters, and the wave function or the partition function will simplify.
Yeah. So good. Yeah, and then right. So then it's over here. Yeah. So it's in the. I think yes, it's on this slide. Good. So yeah, I'm glad that you mentioned that, because yeah, I don't talk about this in math talks. Yes, basically. So this is well, that comes from the Wilson line, that comes from Tooth vortex line, and this is, you can call it dionic line, right? So it's the word line of the dion with 1, 1. Basically, this is that, right? There's an algebra, and yeah. So what Sabir was saying, the so A here is the what is it? It's like the frozen valve. Yeah. So basically, think of X like So
the Coulomb, maybe
the Coulomb branch. Yeah. So if it's some, I mean, it's a 3-dimensional theory, right? So yes, basically it's some frozen valve, some frozen Coulomb valve, right?
Yes.
And for generic values of that valve, well, you have something very complicated. You have infinite dimensional representation. So Z here, of course, is the partition function, is the vortex partition function of this theory, right? Well, SU2, with an adjoint, right? So not this, excuse me. It's T star 1. Yeah, it's partition function of this theory in 3 dimensions.
Yeah.
Of this theory on R2 cross S1. Now the right. So then Q is the omega background that you put on R2, right? And then when you put omega background on R2 becomes this kind of cigar, right? So you kind of spin it around the origin, and you force all sort of field fluctuations to be towards the origin, right? And then there's also a circle. So if you can think of those line operators as points on the circle, right? So it's circle times R2, and then R2 is essentially, you force all your operators to sit at the origin, right? And then, so as you collide them on a circle, you cannot just pass them through. There's a price to pay as you move them around due to the omega background. Yeah, so in fact, and that omega background is related to B field that I mentioned in the in the brain colonization story.
Okay. It's more like epsilon 2 over the ratio of the two omega background product.
Well, I mean, here I'm in 3 dimensions, so there's no second one. Like there's no epsilon 2. So yeah, so Q is like e to the epsilon 1.
Okay.
Like I mean, there is a higher dimensional version of the story, but it's not what I'm. Yeah. So Yegor, does it make it clearer?
Yeah, it's kind of. And do you know the high dimensional? So you just mentioned the high dimensional story. So is there some certainty how it works in high dimension?
I'm not
like
sure.
Not
so
3D, but 5D, for example. Like if you put not on R2 times S1, but
yes, like we have something like R4 with epsilon 1,
right.
epsilon 2, and then try to run the same kind of I don't think it has been studied to the we can expect some generalization of the algebra, right? So but yeah, I don't think it has been studied.
Okay
Good, thank you. Other questions? Okay, good. Yeah, so like I said, I'm really sorry about right now over time. So our next speaker is Yegor. Is it you, right?
Yeah, it should be me. Okay.
Yes, so let's take 2 minutes back, 2 minutes break, and then we'll begin. So just take a couple of minutes to get yourself set up and share the screen.
Sure.
And then
I should share the screen. Right. 1 moment. Let me.
Yeah, we can see your screen.
Good. So that's my first talk using a tablet. So I'm almost, it's almost certain that I'll make some mistakes and like move things around which shouldn't be moved or vice versa. I'm good. Should be fine.
Fox is still here. Are you now in Italy or in Russia?
I'm currently in Istanbul, in Turkey. So I've been in Moscow, but because my daughter have been born 4 months ago and she doesn't have an Italian visa yet. So we had to evacuate immediately because we feared, obviously, for different kinds of things happening in Russia. And so now it's a couple of days we have arrived here, but it's fine. It's fine.
So you can apply.
Everybody's safe.
You can apply for visa for her now, right? So like.
Yeah, hopefully. This is a little bit of a bureaucratic nightmare. So we tried to apply in Moscow and then it kind of failed. And then they said that we have to apply to a different kind of visa because we need for her, it's a long-term stay. So that takes a while to get a paper from the Italian police. Well, okay, never mind. That's that's our.
Let's hope it will get resolved. You managed to
hopefully.
Go, yeah.
No, we should be fine. It should be okay. Yeah.
Okay, are you ready? So shall we begin?
Yeah, I'm ready. If everybody is here, then
yeah, I think folks are here. Yeah, so let's go. So our next speaker is Yegor Zenkevich from SISSA, and he'll tell us about Pentagon identity in dim algebra.
Okay. Thanks, Peter, for giving me the opportunity to talk on the workshop. It's the second one, and the first one was a huge success. So hopefully this one will also be fruitful. So the talk is based on, again, so that's my first try with an electronic tablet because I don't have the blackboard here, sorry. So the talk is based on the paper with the following number, and it is about, well, there are applications, sorry. There are applications of this, but the core is just an identity, it's a mathematical statement. And the statement is probably, well, it's, again, as usual, it's something, well, the fact that nobody cares about something which nobody knew about before. So that's about this quantum toroidal algebra, or also known as Ding-Iohara-Miki algebra, which is a deformation, a certain deformation of, well, there are different ways to put it, but let's say it's there is GL1 double hat. Well, this is all somewhat tied to the previous talk, because so this thing is this algebra is sort of a limit and infinite, well, infinite n limit of AN type spherical DAHA algebra. So the spherical DAHA algebra contains this parameter n, and the limit when n goes to infinity, that's going to be this dim algebra. So and well, it can be defined in many ways and have been actually defined from different points of view. But one way to look at it is that there is this GL1 double hat algebra, which is a sort of stupid algebra. It's sort of a double affinization of the algebra of complex numbers. So GL1 is just C, right? So GL1 is C. So if you take one hat of it, then GL1 one hat is the Heisenberg algebra, what is called the Heisenberg algebra, which is an algebra generated by the modes AN, satisfying this usual commutation relations. And right, something like this. The familiar commutation relations. So that's sort of the first step, the second step, and the third step is to put an extra hat on it, which means that. So what I do here I have a single generator A, and then here I put a hat, which means that I put this modes here.
Yegor, are you there? Did he get disconnected? There you are, yeah. Yegor, you're muted.
Sorry, somehow the internet...
I think you got disconnected. So share the screen again, please.
Yeah. All right. So everything disappeared. Great. I'm sorry. So let me just continue. I cannot rewrite everything which I had. Sorry. So one moment. So hopefully you remember something. So there is this, when you put the second hat, then you get some generators which are numbered by pairs of integers. So n and m. So the pair belongs to the 2. And the commutation relations are very similar to what we have for the single head. So we have the commutation relations like this. There is C1 times n plus C2 times m, where C1 and C2 are some numbers, times a product of deltas. So it's m plus L, n plus k, 0. So this is GL1 double hat, the double optimization. And then there is a deformation of this. So there is a quantum deformation. So this Dinger-Harmicki algebra is what is called UQ, Q1, Q2, Q3 deformation of this GL1 double hat. So from this algebra, I have to deform into something. And this something means that I will have non-trivial commutation relations. So here, in GL1, in the undeformed case, we have commutation relations for generators which live on V2 lattice. So this will remain intact during the deformation. But the important point is that if I have a pair of generators and I take their commutator, it is non-zero only when the generators correspond to opposite points on the lattice, right? So in the right-hand side, the only non-trivial commutation relations appear when I have a vector, a generator of this grading, and another generator of this grading. So that's when the deltas will work out. So after the deformation, I will have something more interesting. So I will have E. Well, let me go to some abbreviation. So I will call gamma a vector. So gamma will be a vector of a lattice. So gamma belongs to Z2. And E gamma 1, E gamma 2. It used to be like this, but now it will contain an extra piece here. So this is going to be, well, some coefficient times E gamma 1 plus gamma 2. And not only this, so plus what it used to be. So let me call this right-hand side here. Let me call it a star. Plus star, plus something. Let me talk about it a bit later. But the important point is that the grading here is respected. You see, so gamma, the left-hand side has gamma 1 and gamma 2. So the grading is the sum of this, and here the grading is the sum here. So I can draw it on a lattice. So if I have, well, suppose I have a vector like this, and the generator sitting here and the generator sitting here. So this will be my, for example, gamma 2, and this will be my gamma 1. So the result of the commutation will be what I will have it here. So this is the vector 2, 2. So this gamma 2 in my example is 2, 1. Sorry, gamma 2 is 2, 1. Gamma 1 is 0, 1. So they will correspond to this E22, and that would be a simple case. So this the non-trivial part is here. So the algebra is a Lie algebra until I consider this part. But this only happens. Okay, so let me talk about this part. So this corresponds to some correction terms like this. Roughly speaking, it's gamma, for example, gamma 1 plus gamma 2 over 2 squared. So this only happens when gamma 1 plus gamma 2 it's non-coprime. So these two numbers are non-coprime. So I can divide by 2 or by some other number and take a power. times again some number. And this makes the algebra nonlinear. It's no longer a Lie algebra, you see. So these two terms, this one and that one, which is here, they're linear. It's a Lie algebra. What makes it truly quantum? So another name of this DIM is quantum toroidal algebra. Quantum toroidal. Algebra of type GL1. GL1. There are GLN versions, but I'm not going to talk about them. So what makes it quantum are these corrections. And these corrections, they only happen, so this number, so this makes algebra nonlinear. Nonlinear. And it is 0 when one of the parameters Q1, Q2, or Q3 is equal to 1. So these parameters are not independent, so it's only convenient to write that there are 3 of them. In fact, only 2 of them are independent. So the algebra is defined for Q1, Q2, Q3 equal to 1. So when one of them is equal to 1, the other 2 become inverse to each other. So Q2 is Q3 inverse. And there is let us call this parameter in this limit. Let us call it Q. Then in this case, the algebra is linear, and we can write what is this coefficient. So just to be familiar with it, because otherwise there are huge formulas for this coefficient in general case, but they are not very elucidating, how to say, because, well, even not all of these coefficients for general gamma 1 and gamma 2 are not known, and also these coefficients. So writing them out is not a good way to introduce this algebra. So let me write it in the limit, when Q1 is equal to 1. So in this limit, this coefficient is Q. It will depend only on this remaining Q. So this will be Q gamma 1, and there are components of this gamma 1 and gamma 2. There is gamma 1 1 times gamma 2 2 minus gamma 1 2 times gamma 2 1 divided by 2. So this is the cross product. So I can write it as a cross product of two-dimensional vectors, gamma 1, gamma 2. So this is the coefficient. In other words, it is a Q deformation, a Q number of this cross product. It's an integer, right? So it's like a symplectic pairing between gamma 1 and gamma 2. And in general, it's very complicated. So what happens? In general, there are these correction terms. And these correction terms, well, one can again, so in general, they're complicated. Let me give a, well, let me give a definition for a limited, some limited case when, okay, maybe it's not a good way to introduce it, but let me just to scare you off a little bit. So if I have gamma 1 and gamma 2, they should satisfy certain properties. So if I have here some gamma 1 and here some gamma 2, so the coefficients are explicitly known in the case when gamma 1 and gamma 2 satisfy certain, how to say, positivity certain elementarity property, which means that there are no, if I consider minus gamma 2 and consider a triangle here, this triangle. Then the commutation relation is known when there are no integer points inside inside this triangle and on at least 2 edges of the triangle. And in this case, the commutation relations will be written using a certain generating function. So let me have another screen. The commutation relations will look as follows: E alpha E beta is equal to 1 over kappa 1. I will introduce the notation a bit later. C So T I can already introduce. So T is this triangle, which I have built from, in this case, alpha and beta, gamma 1 and gamma 2, times H alpha plus beta. And this is when alpha cross beta is more than 0. So what is the notation here? Kappa 1 is part of a series of constants. So kappa n is a number, is a combination of parameters q1, q2, and q3, and they enter symmetrically in this. So the algebra is completely symmetric with respect to permutations of q1, q2, q3. So what is C? C is a combination of central charges, actually. So C gamma will be some C1 power gamma 1, C2 power gamma 2. That's the central charges which appeared in the double optimization. What is M of T? So M of T is the so-called middle of triangle. Middle of triangle T. What is the middle? Well, we have 3 vertices, like 3 vectors in Z2 of a triangle. So say A, B, and C, all belonging to Z2. And there is a lexicographic ordering. Of points on Z2. So the middle of triangle is with respect to this lexicographic ordering. What is H? That's the crucial point. The H will introduce the nonlinearity, because you see, if H were E here, if I had E here instead of H, that would be linear algebra, Lie algebra, right? So H can be introduced by a generating function. Let gamma be a coprime vector in Z2. So a coprime means the 2 components are coprime. And then I have the for every coprime gamma, I have the following generating function, which defines for me this H for non-coprime gamma, because n gamma is a non-coprime vector. So for all non-coprime vectors, I define it as follows. So it is defined through E, and it is a nonlinear combination of E generators. you see there is this kappa k, which was introduced here, ek gamma z minus k. So this h, the h for coprime gamma. So from this we can deduce, after expanding the exponent, one can deduce that h gamma for coprime, for gamma coprime, h gamma is minus kappa 1 e gamma. So after all, it is linear. So if alpha plus beta happen to be coprime, then this, the commutation relations are very simple, because this kappa 1 here cancels with this kappa 1 here, so the minus remains, and this strange central charge term is here, but it doesn't make it more complicated. However, if I have h2 gamma, so this will be nonlinear, because this will involve the square, as I've written on the previous screen. You see, so it contains E2 gamma indeed, but there is a correction term, this one, which corresponds to the square of E gamma. So this E2 gamma by 2, right? So I can divide this non-coprime vector by 2 and square the generator. And in general, this H has become more and more complicated, and all of them involve the dependence on the parameters, because kappa depends on the parameters, the quantization parameters of the algebra. So one can see from this that when one of the q's, for example q1, as I told you, goes to 1, then the algebra indeed simplifies, because kappa, all kappas go to 0. There is a limit where they go to 0. So in that case, the algebra simplifies, and we return to this algebra case. However, in general, it's very complicated, and even writing out the commutation relations for general alpha and beta, which don't form this, recall that we had some important condition that gamma 1 and gamma 2 form this, well, sometimes people call it a quasi-empty triangle. So quasi-empty triangle T, gamma 1, gamma 2. So gamma 1, gamma 2. That's the definition. And only for, so this commutation relations are for quasi-empty, empty T alpha beta. For general alpha and beta, T is not non-empty. If I have, I don't know, arbitrary large alpha and arbitrary large beta with very large components, of course, the triangle which they span, it contains a lot of interior points. But the point is that one can prove that the commutation relations can be defined recursively. At every step, you can use this commutation relation for quasi-empty triangles, and then everything boils down to them. But in general, there is an algorithm, but it's a kind of combinatorial problem, and there is no explicit formula. There is no explicit formula for the commutation for general alpha and beta, but there is an identity which is the subject of my talk. There is an identity which involves arbitrary large values of alpha and beta, which is still tractable. So this is the Pentagon. Let me give another piece of screen. The Pentagon identity. The Pentagon identity. Well, you are probably familiar with some version of Pentagon identity. For example, for quantum dilogarithm or non-quantum, just ordinary dilogarithms. And I'll get to this, because this, well, more conventional type of Pentagon identity will turn out to be a consequence of this Pentagon identity in the dim algebra, for the generators of the dim algebra. So let me state the identity. That's the conjecture. So, conjecture. So I will talk about the arguments in favor of this conjecture and what follows from it. Okay, so let me introduce T gamma, a generating series involving E generators. Oh, by the way, so this algebra, the dim algebra is important in many applications. And for example, this AGT story, it more or less rests on the existence of this dim algebra and on certain properties of it. Because, well, there are automorphisms of this algebra, which I'm again, they're not crucial for what I'm going to talk about, but they're crucial for this gauge theory / CFT connection. And well, in general, it is very much tied up with instanton calculus in particular, and its generalization. So I introduced this combination T gamma of generators. So gamma can be any vector in Z2, well, non-zero vector in Z2. And then it turns out that following from that implicitly defined commutation relations, so well, I've only defined explicitly commutation relations for certain generators E, but from these commutation relations, it follows the following identity for T. Which is precisely the Pentagon identity as it is. Well, it is it has very familiar form of something times something is equal to triple something. So here these operators, they all don't commute, and the identity is quite non-trivial. So this is the conjecture. What are the arguments in favor of this conjecture? Well, there are arguments in favor. Well, I don't have any arguments against it. So, well, no, I do have one. Anyway,
you can prove it for Q3 equals 1, and then conjecture for Q1, Q2 generic, or is even for in that case.
That's one way. So you can so the first one is you say Q3 is goes to 1. Then it's an identity in a Lie algebra. So this is one. This is actually one of the simplest Kontsevich-Seibelman identities. So wall crossing identities. Sorry, it's how it is called, motivic wall crossing identity. So in that case, what is the identities? And the identity in a Lie algebra. So we have a Lie algebra, as I've told you. So the commutation relations, they become linear. Becomes a Lie algebra of functions on a quantum torus. On a quantum torus T to Q, where Q is this remaining parameter. And then there is there is a conjecture that there is an identity precisely for this form of this combination, the generating functions of elements of an algebra of functions on the quantum torus. So of algebra on the quantum torus. So how does it work? Let us go back to yeah. So here I have this coefficient you see in front of e gamma 1 plus gamma 2, or more compactly written here. And that's precisely the non-commutativity of the quantum torus. So if e gamma 1 and gamma 2, they correspond to the elements in the quantum torus. If I have the generators of the space of functions like x and say p, which don't commute, then this e gamma would correspond to this sort of product. And then the commutation relations will look like this if my x px is equal to q xp. That's the non-commutativity of the coordinates on the torus. So x and p are coordinates on the torus, and then there will be this precisely this algebra. So that's the case of wall-crossing identity, which is proven. Again, it's not a completely trivial identity, even in the algebra. So it involves an infinite number of generators, but it's true. It's known to be true already. What happens? Well, then we ask what happens for non-trivial Q1, Q2, Q3. We need to make some checks for non-trivial Q1, Q2, Q3. The first check for generic. So the second bunch of tests is for generic Q1, Q2, Q3. Well, the product is 1, but otherwise generic. One can try to evaluate this identity in representations. So many representations of this dim algebra are known, as you can imagine. And let us, one can try to evaluate it in some known representations and see if it is true. And 2a is try to evaluate it in the simplest so-called vector representation. Vector representation of the dim algebra. There are 3 of them, 3 of these representations, which we call VQI. So there is a VQ1, VQ2, VQ3. So in these representations, E gamma for general gamma is expressed through the elements of quantum torus. But the quantum torus, there are 3 of them. There are 3 non-commutativity parameters, and one can use any of them. So if you have in VQI, you have Px equal to Qi xp, and then E gamma in this representation is written like this. Qi gamma 1 gamma 2 divided by 2, and here it is Qi to the power greatest common divisor of gamma 1 and gamma 2, the components of gamma. So this is, oh, sorry, there is a minus here. Times x gamma 1 p gamma 2. That's exactly the algebra. Well, that's the algebra of functions on the quantum torus. But there are three different types of them. And it turns out that this is a representation also of the deformed algebra. But the important point here is that this x and p, so this E gammas, they satisfy some additional multiplicative relations. So if I have, say, E alpha times E gamma in this representation, so let me call it this representation rho. So in this representation, rho Qi, so if I have a rho of E alpha, rho of E gamma, this is proportional to rho of E alpha plus gamma. So there is in the representation, for operators in the representation, there is an additional multiplicative relation, which is not present in the algebra. Well, in a generic representation. In a generic representation, you can only take the commutator, and there is some relation for commutator, but the product of generators is not equal to generator again. But here it is, as you can see from this. So this is simplifies the calculations a lot. Well, you can see that there is an expression for generic gamma, so for generic generator, and one can prove that it still satisfies this deformed commutation relation, this horrible deformed commutation relation. But this is because of this relation which simplifies everything. And what happens to our identity in this representation? Well, it becomes, so let me call it somehow, I used to have a star, so let me call it double star. So double star becomes Faddeev-Volkov standard commutation relation, standard Pentagon relation for quantum dilogarithm. Faddeev, Kashayev, Volkov. Volkov identity for quantum dilogarithm. So one can see that T becomes T gamma becomes well, x gamma 1, p gamma 2, qi infinity, the Polynomial symbol, more or less. Well, there is some inverse here and minus there, but otherwise it is like this. So, and this is true. Well, of course, everybody knows that the Faddeev quantum dilogarithm satisfies the Pentagon identity. Well, okay, that's good news, but we can go further, and we have another check. Well, there is a more complicated representation where this simplifying relation doesn't hold, and this is the Fock representation. The Fock representation of the dim algebra. In this representation, what happens? So we have E. Well, there are. It is a representation on the well, on the space of symmetric functions, basically. So F, the Fock space of a free chiral boson, is the space of polynomials in an infinite number of variables, P1, P2, P3, etc. And one can consider different bases in there, like Macdonald polynomials or anything, but it's important that it's just the space of polynomials. So how does it work? Let me give an example of generators in this representation. Let me call it F, this representation F. So in this representation, I have, well, there are again 3 types of this F representations, depending on the choice of one of the Q parameters. So let me write here, say Q2. So for positive n, it is like this. For negative n, well, minus n, it is the multiplication. Well, it's minus here. Well, there are some formulas, and just I'm not going to write all of them, but there are some formulas for the generators. That's again for n greater than 0, but it's a negative generators. So this part of generators, if I draw this lattice of generators, so this E01, E02, etc., they sit here on the vertical axis. So the generators on this vertical axis, they form a Heisenberg algebra. And all other generators here, well, I have a whole plane of them. In general, they're in the algebra, they're separate generators, they're independent generators, all of them. But in this representation, in this Fock representation, they are expressed as vertex operators, depending on, so this expressed through Pn and d by dPn as vertex operators. Sorry. So they're not independent in this representation, but still it's more than well, it's a more generic sort of representation than the vector one. I have more independent generators. For example, E02 is no longer equal or no longer proportional to E01 squared as it was in the vector representation here. So here we can see that they are independent. They correspond to different P's. So what happens to our identity, the Pentagon identity? If I evaluate it using, so I act with F, sorry. So this F acts on Pentagon, sorry. How do I do this undo stuff? No. Impossible, okay, fine. If I act on this star, what do I get with this F? Well, I get an identity for some complicated operators depending on Pn and d by dPn. And it's convenient to evaluate it in the basis of Macdonald polynomials. Of course, it's not essential. Well, it doesn't depend on which you act, because it turns out that this identity is true. And this identity was discovered in the work of Garcia and Anton Mellit, several years ago, like 5 years ago. And it's an identity, they also called it a Pentagon identity for operators, well, related, sorry, to Macdonald-Hamiltonians. Well, the thing is that this vertex operators through, well, which provide the representation of this other columns in the plane, the further columns in the plane of generators, they are expressed through Macdonald-Hamiltonians. And so are T's. So this T gammas, they are expressed through Macdonald-Hamiltonians and also through multiplication by Pn and the differentiate, well, the derivative with respect to Pn. And so this identity is true. It's a theorem. There is a kind of combinatorial proof. I didn't follow it completely, but it's a proof. So this is known to be true. That's already something. So we have an identity which, well, first of all, in the limit it is true. It is also true in two non-trivial representations of the algebra. So now we start to think that maybe it has some chance to be valid abstractly on the level of the generators of the algebra. And one can try.
Pn are symmetric polynomials in x to the n, right? Like in Macdonald, they symmetrize, power symmetric.
Right, but the number of xn is infinite, so I express.
Right, yeah, I understand. Yeah, but like for say for fixed.
So that's another. So yeah, so Pn is something like sum of xi power n. So these are power sum generators, and here it is n, which goes to infinity in this case. There is also a representation when n doesn't go to infinity for finite n. It's a bit more tricky, but That's basically where well, there is a homomorphism. There is a homomorphism from dim to DAHA for finite AN. So
in fact, I was about to ask that. So when you truncate this module, like truncate dim to DAHA, what happens with the pentagonal identity?
It's a non-trivial identity. It's a non-trivial identity again for Macdonald-Hamiltonian, but this case not for infinite number of particles, but for finite number of particles.
I mean, does it look like pentagon still, or is it?
Yeah, it does. It does. So this, what do these T's do actually? So we have T10 and T01. So one of them, this contains E0n, right, in the exponent. So this E0n, they're here. So they're the derivatives with respect to Pn. So they differentiate. They turn Macdonald polynomials into other Macdonald polynomials. Well, you can use something like QT whole Littlewood rule.
Maps to some other element of the basis. Yeah. Okay.
Yeah. And these T10, they contain En0, which are proportional to Hn, the Hamiltonians, precisely the Macdonald-Hamiltonians. So these act diagonally, and I have a combination, and a funny combination of this when I try to commute them. In general, it's not trivial, but then one can try to commute, and one learns that the Pentagon holds.
But whatever stands in the middle is not going to be T11. It's going to be some mess, right?
Yeah, but T11 is something. That's another piece of art, how to write T11, because it's neither just multiplication. So T11 is neither just multiplication by Pn or the derivative, nor is it a Hamiltonian which acts diagonally. So it's something else. So the clever way to express this, that's a piece of like a technical piece, but nice. So the clever way to express T11 is with the help of this T nice or tau, let me call it tau, automorphism through T01. So I have T which belongs to SL2Z. SL2Z acts on the algebra in general, but in this case, it's also acts in the representation space. So this T is well, it's a certain can be expressed in the basis of Macdonald polynomials. So this tau, this tau acts on n lambda with something like this. There is a product of the cells of lambda. Sorry for this technicality. X. So here it is something like J minus 1 Q2 I minus 1 m lambda diagonally. So there is this operator which is diagonal in the basis of Macdonald polynomials with this eigenvalue. And it turns out that it is precisely the T element of SL2Z. It provides the action, SL2Z action automorphism group of the algebra. That's on the representation. The representation remains intact, and there is an operator tau like this, kind of inner automorphism in this on the algebra of operators. So after this, one can express this T11 in the basis of Macdonald polynomials, and that's what they do. And this can also be done, of course, for finite n. This can also be done. There will be some identity, a non-trivial identity. I haven't checked it, but one can try to check it. That's a good problem. And finally, let me just, before my time is completely is up, let me write the third argument. That's a brute force check. Brute force check. For generic Q1, Q2, Q3, one can just try to do the algebra, well, to do the commutation relations, and try to check in different orders. So I have this T10, T01. So where do my generators lie? My generators are in T01, they lie here. In T10, they lie here. And I have a generating function, and then I need to commute them. So I commute, in general, I have all possible pairs, but what I get is something which lies here, right? And I can check, so I have a product of these guys in this, oh, I don't remember, sorry. I guess it's reversed, but never mind. The correct formulas are in the paper. So if you multiply them, you get all possible, in every, at every grading, you have some expression. Like the product of some generators, the sum of different products of a given grading. And you can check start checking in all of these cells and all of these vertices, you can start checking if the left-hand side is equal to the right-hand side. And this is non-trivial because, as I said, the commutation relations are implicit. In general, they are implicit. So you cannot simply commute the generator sitting here with the generator sitting here. You need to express them through through the primitive vectors, through more primitive vectors, so that the commutation relations are for this quasi-empty pairs of vectors that form quasi-empty triangles. But still, one can pursue this, and with some help, one can check this small area just by hand. This small area can be checked, and this is still very non-trivial. For example, let me give one final example how this works. So the term which is the term u squared v power 1 rests, well, the validity, okay, let me write this one. So this is the really non-trivial one. U squared v squared, it requires the following commutation relation: E20, E02. You see, so this don't form a quasi-empty triangle because so these are precisely what I was talking about. These are these two vectors, and the triangle, it does contain points on all the edges. So this is, in principle, one needs to work to get this commutation relation, and the answer which is needed for the relation to hold is like this. And of course, after a bit of algebra, one learns that, so here is E22. One learns that this is true. And this is completely non-trivial. And also another interesting point is that, so I have this is equal to T. And as you can see, neither T nor any, well, there are the spectral parameters, but they're arbitrary. They're just related to grading. So neither the T doesn't contain Q1, Q2, Q3 inside. But the commutation relations do contain them. So there is this kappas all around, which depend on Q1, Q2, Q3. And they, if you do the commutation relations on the left-hand side and on the right-hand side, you obtain a large number of these kappas, but then they cancel between two sides. So this remains true. Okay, so this I can write some applications and implications. So to wrap up, so the applications. Well, one can write as Peter rightly pointed out. One can write this Pentagon relation for spherical DAHA too. So in spherical DAHA.
So what it will be for rank 1? Like from my talk, like what's is it
yeah, rank 1 is we are back to vector. Sorry, rank 1 is something. Rank 1 is something. Yeah, it's well. one needs to look at it. It's non-trivial. Some commutation relation between if you multiply by x plus x inverse, something like this, and then you have the Hamiltonian, and you take some combinations of this, some function here, and some, I don't know, another function here, and then you try to compute them. You get this sort of Pentagon identity. It turns out.
I see. So H1 is Macdonald, right?
Yeah. H1 is this Macdonald difference operator. The second one is the first one is because we have a homomorphism into here from the algebra DAHA of n, circle DAHA of n. The second one is for more non-trivial representations. If I have there is the so-called McMahon representation. This is a representation on 3D Young diagrams. It is superficially similar to this Fock representation. In particular, there are these Hamiltonians Hn which act on the states which are labeled by 3D Young diagrams pi. So I have states labeled by this pi, and Hns, they act diagonally. We have some I don't know, lambda n of pi times pi. So they act diagonally. There are the Hamiltonians, but there are also operators which add boxes and remove boxes. And one can build this T, the generating functions, out of these operators and check if this is true on 3D Young diagrams. That would be a new identity for operators acting on this space on this McMahon space, on the space of labeled by 3D Young diagrams. So there will be another another non-trivial identity. And the third, so it's not an application, but more a question. So how does this identity, how does double star, how double star is compatible with the coproduct? With delta, the coproduct, because the algebra, the quantum algebra, it contains, it has a coproduct, a non-trivial one, and it turns out that naively this coproduct does not respect this pentagon identity. Well, it's not that it doesn't respect it; it's non-trivial that it respects it. The left-hand side doesn't go into the tensor product of two left-hand sides. So it's not that, so the problem is that in general, delta of T of gamma is not equal to T of gamma tensor T of gamma. Well, for some gammas it does, but for some others it doesn't. Well, there is another story which I'm not going to go deeper because there are many coproducts actually, an infinite number here in this algebra. There is an infinite number of coproducts labeled by slopes and the Z2. And for gamma parallel to this slope, this is true, while for non-parallel, this is not true. There is a more complicated. The action of coproduct is more complicated. So how it works, if it is more complicated, and how the identity still holds, is a mystery for now for me. But it seems to work in all these representations, and it some brute force checks are also true. So I believe it is true, but how it works with the coproduct, I wish to know better, and maybe it sheds some lights on the properties of this coproduct. And the final point is the physics applications. Is that probably this all what this all means is that this beam algebra is the algebra of BPS states. So this algebra of BPS states in string theory. And the identity, the commutation relations is some sort of wall crossing for the states, wall crossing identity for the states. But this also is it requires further thinking. So how it all works. So presumably it's something like a wall crossing for PQ strings. So if I have this T gamma, that should correspond. Gamma should correspond to PQ charge of the string. Okay, so for now,
but it's the topological string that lives sort of on the other side of geometric transition, right? So once you, I mean, it's not So like it's a resolved conifold kind of construction. But yeah, okay.
Well, it's a refined topological string. That's the algebra of refined topological string, but probably it's more like I don't want to go further. But it looks like there are more states to it, and it has something to do with the physical string theory, probably. But for now, I don't have anything concrete to say here. Okay, so I stop here if there are any questions.
Thank you, Yegor. Are there any quick questions? We're running a little bit over time, so is there anything folks you can ask? I don't see any. Okay, so thank you very much again. And we're moving to our last talk of the session by Andrey Zotov. Andrey, you ready?
Yes, I'm here. Yes.
Good, yeah. Let's share the screen. See how it works. And we can wait for 1 minute and then we can. Yegor, I think you need to quit sharing from your side, and so Andrey can do his.
Right, sure. Let me do. Sorry, yeah. So I stopped this one. Okay, good. Now it is.
So while we're waiting, so all the speakers, past and future, please email me your slides, and I'll put them on the website. And video recording's already there, so we can.
Can you see it now?
Yeah, we can see that.
Okay.
You want to go like this or with a full screen?
Oh, just a second. Okay, let it be like this. Okay.
Yeah. I think that's better now.
So, should I begin?
Okay, good. So let's begin. Our next speaker is Andrey Zotov from Stiklov Institute, and he'll be talking about spin generalization of the elliptic Macdonald-Ruijsenaars operators and the elliptic version of q-deformed Haldane-Shastry model.
Okay, thank you very much. First of all, I would like to thank the organizers. Many thanks to Petya Koroteev and Slava Spiridonov for this conference. And my talk is about spin generalization of elliptic Macdonald-Ruijsenaars operators and an application to elliptic version of q-deformed Haldane-Shastry model. The talk is based on two recent papers, joint papers with Masha Matushka, and here references are given here. And the plan of the talk is as follows. First, I briefly recall some basic definitions and some basic facts about Macdonald-Ruijsenaars operators, which I need in my talk. Then I proceed to the main part of the talk, which is a construction of spin operators and underlying R matrix identities. Then I briefly discuss classical analogs for these models, and these are kind of relativistic interacting tops. I will explain later. And finally, I will show a nice application of these results. They allow to construct elliptic integrable long-range spin chains using the so-called Polynomial freezing trick. So let us begin. Here are some notations. The pi I shift operators acting on some functions by the shift of corresponding arguments by minus eta. We're going also to use the elliptic Kronecker function, which is a ratio of theta functions, and theta function is it is the one which is the odd theta function, which has simple 0 at 0, and this ratio is very famous in integrable systems. It is widely known. It appears in Lux pairs, R matrices, and so on. So it's the standard ratio of theta functions. And using these notations, we can formulate the result proved by Ruijsenaars as follows. Consider the following set of operators, and these operators are called the elliptic Macdonald-Ruijsenaars operators, and then these operators commute. Here, the sum is taken over overall subsets I, subsets of indices from 1 to n. And here is the product of shift operators and some products of pi functions. And in the trigonometric limit, using some simple definitions, one can reproduce the also widely known Macdonald operators. So they are also included into this family. And for example, the first Macdonald operator is given here. It happens because for the first operator, this subset I large consists of one index, and here we have, I'm sorry, and here we have the difference of arguments. One argument belongs to this subset.
Is that the cat?
Yes, this is my co-author of all my papers, in fact. And so one index belongs to the subset I, and another doesn't belong. And for the first Hamiltonian, we have the I, which consists of one index, and this is why the following expression arises. And this is also can be seen as the first Hamiltonian of the trigonometric Ruijsenaars-Snyder model. And in the elliptic case, in the elliptic classical case, it looks like as given here, and this is the Hamiltonian of elliptic Ruijsenaars-Snyder model. And it also can be easily degenerated in the non-relativistic limit to Kalodzer-Motor-Sutherland model, which describes interactions of n particles on the complex plane with the potential given by the Strauss pi function. So this is just a remark that the problem I'm discussing is related to many body systems, and these many body systems of Kalodzer and Ruijsenaars types are known to be generalized to spin case. And for example, spin Ruijsenaars-Snyder model was introduced by Krichever and Zabrodin. And we're going to deal with this type of models, but in fact, we're going to deal with anisotropic versions of this model. And I will explain later what I mean by the word anisotropic. So let us come back again to Ruijsenaars-Macdonald operators, and let me recall briefly the main construction from the Ruijsenaars paper and how to prove commutativity of these operators. Let us introduce the following notation, the following short notation for the product of pi functions. And the following notation for the product of shift operators is just using this notation. The operators are written as given here. So this is just the product of functions, and this is the product of shift operators. And we also introduce the same notation with plus minus, which means that the corresponding indices are shifted. For example, I plus means that all variables that I are shifted by minus eta, and I minus means that they are shifted by plus eta. So then, in his original paper, Zenkevich showed that the commutativity of operators is holds if and only if the following set of identities hold true. In fact, commutativity of Macdonald-Ruijsenaars operators can be proved in several different ways, using Cherednik operators or in some other ways. For example, Koroteev showed gauge equivalence of Ruijsenaars model to Sklenin type operator, Lux operators, and it can be also used to construct commutative families. And so there are several different ways to prove it. But what I need in my talk is the original one proposed by Ruijsenaars, where he showed that the commutativity is equivalent to the set of identities. And one can just verify that the elliptic phi function indeed satisfies all these identities just by analyzing the structure of poles and zeros. And moreover, he showed that in a class of meromorphic functions on elliptic curve, the solution given by elliptic Kronecker function can be seen as a single up to some factors, some exponents, which are don't change this function too much. And here are also trigonometric and rational versions for this phi function. They also satisfy this set of identities. So our purpose is to construct spin generalization for these operators, and we're going to prove their commutativity in the same way. We're going to derive a set of identities and then prove it. In order to construct
Andrey, can you show the slide with definition of I, please, one more time?
I?
Yeah, the one.
Yes, wait. These are two just disjoint subsets in the set from 1 to n.
I see. So just the pair of indices. Yeah, good.
Yes.
Thank you. Thanks.
The pair of sets of indices, and this brackets means the product of the corresponding function, where the I small is from I and J small is from J.
Thank you.
Yes, and this just exactly the product which stands here, but one of the subsets here is a complement of another one. So the unification is a full set from 1 to n. Okay, now in order to construct spin operators, we use constructions which are known from early papers by Wolf, Cherednik, and some other people. And most clearly, this recipe was formulated in a recent paper by Liners, Pasquier, and Serban. And we're going to use their recipe to construct the spin operators. And for this purpose, we need to recall some basic facts about quantum R matrices. A quantum R matrix is a solution of quantum Yang-Baxter equation, which is given here, or equivalently, it can be written in this form for any three distinct indices. And then any R matrix is a linear operator on the following Hilbert space. It is It is a tensor product, nth power of tensor product, and our matrix acts Rij acts on the eth and jth components of this tensor product. And for example, if we consider a pair of our matrices with all distinct indices, they commute because they act on different tensor components. And in my talk, I'm dealing with elliptic JLM Baxter-Belayon R matrix, and we're going to use two different normalizations. The first normalization comes from the following unitarity condition. So here we have identity operator in the right hand side, but it is multiplied by the product of phi functions. And another normalization is given here below. It differs from the previous one just by this factor, which is phi function. You can divide the R matrix by it and then obtain just identity operator in the right hand side. So it is very simple, but it is going to be important in what follows, so that we use both normalizations. Okay, now let me just show, just recall that in M equals 2 case, we are dealing, the elliptic R matrix is the Baxter R matrix for the 8-vertex model, and it is given here explicitly. And our consideration also includes different types of trigonometric and rational degenerations of the elliptic R matrix. They were considered first by Cherednik, who found 7-vertex trigonometric R matrix and 11-vertex rational R matrix. And the higher rank analogous was found by Antonov, Kosegawa, Zabrodin, and Andrey Zotov, and some other people. And the most simple case, the most simple degeneration is given by the rational Young R matrix, which is given here for one normalization and another normalization. This one is normalized to just identity operator, and this one provides some additional factor. Yes, and in this case, we'll, for example, for the rational R matrix, we'll obtain expressions for quantum Hamiltonians of rational Spin-Rosener's model, and we'll come back to it a little later. So let us discuss the construction of spin operators. For this purpose, consider a symmetric group generated by these relations. These are braid relations, and this is involution property. And so any element of a symmetric group can be constructed by means of these generators. So that it is, in fact, has a very simple representation, which is given here. It means that each generator corresponds to permutation of neighbor arguments for some function, and an arbitrary element from the permutation group then can be constructed as a composition of these elementary operators. For example, the cyclic permutation is obtained as a composition of this S12, S23, and so on. And let us also introduce the following notation, which means that we look for an element of permutation group. Okay, just a second. Consider the increasing set of indices and define such element of a permutation group, which maps the values of these indices to their numbers. And this element is easily written in terms of product of cycles, and each cycle can be also in its turn written as given here. Then what we are going to do with this, we are going to represent the Macdonald-Ruijsenaars operator in the following form. Each operator can be can be viewed as a sum over certain permutations acting on some first term. This term can be can arise from some fixation of subset I0, for example, as given here. It means the following. It means that we all the terms in this operator, since they are symmetric with respect to permutation of arguments, can be obtained from the first one by some by action of permutation group, and this is what is given here. So we have some first element and the action of permutation group, and now the sum is over elements of this permutation group. And let us come back to that Braid relations with involution property and recall that there is another well-known representation for these Braid relations, which is given by the product of R matrix times permutation operator, where permutation operator is a matrix permutation operator. Here we had the permutation of arguments of functions, and here we have the permutation of tensor components of this Gilbert space, vector Gilbert space. So it's widely known that this expression indeed satisfies this condition just due to Yang-Baxter equation, and the involution property arises if this R matrix is unitary, and this is our case, so it also holds true, so that we can now consider a composition of the previously discussed representation. So it consists of permutations of arguments, permutation of vector spaces, and R matrices. And for example, if we need to write down an element corresponding to cyclic permutation, then we should consider the product of such expressions, and then we get some permutation element in the vector space, some permutation element in the arguments space, and some product of R matrices. And if we substitute this representation into these decay operators, then we obtain some expressions which look quite complicated. I will explain a little later, but what is written here? So the expressions in the brackets are those exactly the products of phi functions. Here is the shift operator, and it is conjugated by some elements which are constructed as given here. And after so using the properties of permutations, one can see it can be shown that the permutations of arguments and permutations of vector spaces can be cancelled out, and then we are left to the just difference operators, which have this factor which was originally in the scalar case, and also we have the product of shift operators conjugated by some products of R matrices. And it is important that these R matrices are normalized as we had here. These are R matrices with bears, and so for in scalar case when m equals 1, these barred R matrices are equal to 1. So all these expressions are vanishing in this case, and we come back to the original scalar operators. So the scalar case is included as the simplest case in this formula. Okay, now now let me, in order to comment, I'm sorry, how much time do I have?
I think like 20, yeah, that's 25 minutes, even more.
Okay. in order to prove commutativity of such operators, I emphasize that this is just a result of construction. So this expression which we obtained, they do not commute. I mean, if you just, or at least it doesn't follow from this construction. This is just a way to construct, and on the next step you need to prove their commutativity. And in order to do it, we need we may use another set of useful notations. We define a product of our matrices, like given here, which consists of ordered products. So when the arrow looks to the left, it means that the corresponding index is increasing. Sorry, it is decreasing, and when the arrow looks to the right, then the corresponding index is increasing. And by rearranging these indices, one can also show that this expression is equivalently written in terms of products with inverse arrows. So, and this doesn't the equality between this expression doesn't use Young-Baxter equation. It just uses the fact that you may it uses the following fact that when all indices are distinct, then you may just move one matrix through another one. So it's a quite trivial statement, but it also may be useful and important. And in these expressions, the index I is less than j. And if we also add another primed notation which is very similar to the previous one, but when I is larger than j, then we can say that the product of R and R primed is our matrix analog of for the notation of Ruijsenaars, which was denoted as I and j in the brackets. So if we just consider a product of R prime times R, then we get this type of expression. And in the scalar case, it is exactly the product of phi functions, which was used by Ruijsenaars. And up till now, we didn't use the quantum Young-Baxter equation. And so these notations allow us to write it down in a very compact form. And it is formulated below. Consider any distinct subsets ABC, then the following identities holds true. And these identities, in fact, encode the quantum Young-Baxter equations. I couldn't find these relations in literature, but I think they are known. But just to comment, they are very similar to what is usually used when studying fusion procedures, because when you study fusion, you consider a product of our matrices, and these products also satisfy some relations of Young-Baxter type. And this is similar, but also not exactly coincide. Okay, and also in these new notations, we may write down unitarity property, so that the product of R and R prime is equal to identity operator multiplied by the product of phi functions. And if we use the Baird R matrices, then there are no coefficients here, just an identity matrix. Okay, and so the statement is as follows: that the spin operators we are looking for are of the following form, which is given here. And here is the product of phi functions, and here is the product of shift operators, and the shift operators are conjugated by some of these huge products of our matrices, which came from from that representation of permutation group. And here are some examples. For n equals 2, we have the first term here remains as it is, and the second term is obtained from the first one by the action of permutation group, and this permutation group leads to these R matrices. And similarly, for example, for n equals 3 case, we begin with the first term, and then act by permutation group, substitute representation I told about, and then obtain the following expressions. Each time the shift operators are conjugated by some products of R matrices. And here is also example for n equals 4, and so on. Okay, the main statement at this step is the following. The operators, the spin operators commute with each other if and only if the following set of identities holds true. And it is important that in these identities, the R matrices are those without bars. So the operators themselves depends on R matrices with bars, but these 5 functions cannot be included into these R matrices to transform to R matrices without bars. But when you consider the commutator and derive identity, it appears that all 5 functions can be included into R matrices so that they are normalized as through 5 functions. It means that, for example, this is an example of the identity in the simplest case, n equals 3. And what I just told means that in the scalar case, you may just replace R matrices with 5 functions and obtain the set of identities which were found by Ruijsenaars. But here we have some kind of non-commutative or matrix generalization for those identities. And here are example for n equals 4 and k equals 1. K is the size of this subset I. And for example, for k equals 2, it grows fastly the complexity of this identity. And when we found it, we just tried to verify it numerically, and found that they indeed fulfilled. And then we proved it just straightforwardly by hands, just using some similar idea which was used by Ruijsenaars. We suggested the proof by induction, but it is of course much more complicated. So our first paper, it's about 40 pages, and all this paper is devoted to derivation of these identities and the proof of these identities. So I'm not going to go into details. I just make a statement that these identities can be proved. Okay, now let us talk a little about what kind of many-body systems we are discussing. When talking about many-body systems in classical mechanics, we usually deal with Lux pairs with spectral parameters, and this is an example, widely known example found by Koroteev for the Lux representation with spectral parameter for elliptic algebra model. Here's the Lux matrix. It is n by n for n-body system. And this nu is a coupling constant, and phi is the phi function, the elliptic phi function which I previously used. And the phi function is fixed, in fact, by its quasi-periodic properties and by its pole structure. It has a simple pole in z at z equals 0. so it satisfies this equation. And the Lax matrices can be also fixed by some periodic, quasi-periodic boundary conditions on elliptic curve, and some residue at z equals 0. So in this respect, the Lax matrices can be considered as sections of holomorphic bundles on elliptic curves, and the boundary conditions are in fact the transition functions of the corresponding bundle. And this viewpoint allows to classify elliptic models by using classification of underlying holomorphic bundles over elliptic curve, and it was mentioned in some way by Gorsky, Nekrasov, Levin, and Bolshanetsky, and then it continued in further works. And let me just give an example when, yes, the classification of holomorphic bundles is known from very old paper by Atiyah. And for example, for holomorphic bundles of degree 0, we have the following transition functions, and they lead to the spin-Calogero-Moser model, which is given here at classical case, and at quantum case, this product of spin variables is quantized to the permutation operator, which is given here. In this way, the spin exchange operator appears in quantum spin Calogero-Moser model. And if we consider the degree 1 bundles, then I don't have time to go into details, but in this case, we use some different matrix basis, which is used in Belanin's quantum R matrix. And finally, this leads to the Sklanins type Lax matrix, and everything works here. And the underlying mechanical model is a kind of integrable top with a special inverse inertia tensor J, which is tangent P and the commutator. But there is an intermediate case, and this also follows from that Atiyah's classification of holomorphic bundles. It corresponds to the case when the rank is a product of n by m and the degree is equal to m. And in this intermediate case, the model of interacting tops arises. It's a kind of mixture between the tops and many-body systems. And this intermediate model is described by the following Hamiltonian. It contains the sum of n Hamiltonian n of n tops, and these tops are moving with momenta pi I and interact with each other somehow, non-trivially. And the Lax representation also exists. It is given by nm by nm matrices, and it has natural block matrix structure. And when m equals 1, it is the top model, and when m equals 1, it is the spin Calogero-Moser model. And all the same works can be lifted to relativistic case. I won't go into details also here, but just I want to say that this story can be lifted to relativistic case, and one can write down Lax pairs, equations of motion. And for example, here we have equations of motion where S, Ij are themselves matrices, but in m equals 1, m by m, all these S's are m by m matrices. But when m equals 1, this equation reproduce equations of motion introduced by Krichyshvili and Zabrodin for spin-Ruijsenaars-Schneider model. While when n equals 1, we come back to relativistic top, which in fact is just a classical Sklanин algebra. So now yes, this was just to remark. This was just to remark that the classical analogues for the models we're discussing are known, and what I want to say is that the model which we constructed, the spin operators, is a quantization of this model of relativistic interacting tops. This statement needs to be proved, but I expect that it is, and I will show a little later some additional arguments. But let us now talk about important application, and the application to long-range spin chains. The long-range integrable long-range spin chain, the first non-trivial example, was introduced by Haldane-Shastry, and it is given by the following Hamiltonian, where pi ij are permutation operators acting in vector space. And here is inverse squared sign, which argument is xi minus xj, and x's are equidistant points on a circle. So this model describes n spin being attached to equidistant point on a circle and interact with each other by spin exchange potential. And this is, of course, can be extended and generalized to some different Lie algebras and so on. And for example, for JLM case, so for SU2 case, we have the permutation operators given here, and similarly, it can be written for JLM spin chain. Then the permutation operator just acts on n-dimensional spaces, components of tensor products. Okay, and now we need to recall what is known as Friesen trick. It is a relation. So of course this expression resembles the expression for the Hamiltonian in the spin in the quantum spin Calogero-Moser model. Only kinetic part is absent, and the positions of particle are fixed to equidistant points. And the statement which relates the spin Calogero-Moser models with long-range spin chains is known as Polynomial Friesen trick. In fact, originally he introduced his procedure in order to solve the corresponding quantum problem, and we don't discuss solution of quantum problem at the moment. So that for our purposes, we may say that the Friesen trick is as follows. Consider the quantum spin Calogero-Moser Hamiltonian and consider the corresponding spinless classical model. So here we have spins, and here we have a quantum model, and here we have classical model and no spins. And if we find equilibrium position in this classical model, suppose we find them, and these equidistant points are indeed equilibrium positions in trigonometric and elliptic Calogero-Moser models. And if we substitute these positions fixed to corresponding equilibrium positions here, and remove the differential part, then we obtain the Hamiltonian of Haldane-Shastry type. Of course, this recite is just a recite, and it should be proved that it is indeed work. So, and it should be proved, for example, that if the spin Calogero-Moser Hamiltonian compute, then so do the long-range spin chain Hamiltonian. And this can be done. This can be done, and this is what is called the Polynomial Friesen trick. Similarly, we can, of course, apply the freezing trick to anisotropic models. What is an anisotropic model? Isotropic model is then, for example, this one, when we have permutation operators here. And by anisotropic models, I mean that the interaction depends on internal indices as given here. And in very particular case, when this expression is proportional to Kronecker symbols, then it turns into the product of permutation operator times by some potential. But in general case, it is not. And for example, here is an example of integrable xx z J2 model, and it is it is anisotropic in the sense that there is a coefficient which stands behind products of sigma 1 and sigma 2, but the coefficient behind sigma 3 is 1. But all this, all what I just told was about non-relativistic models, and we're dealing with relativistic models in this talk. And this is why we proceed to the so-called q-deformed Haldane-Shastry model, which was introduced by Oglov in 90s, and in the recent paper by Liners, Pasquier, and Serban, his construction was revised and very much clarified. And we use the result here and to write down the first Hamiltonian of the Oglov's chain. Oglov's or q-deformed Haldane-Shastry, it's just the same. And this is given here, and it is indeed a generalization of Haldane-Shastry model in the sense then that if t goes to 1, then one can reproduce the Haldane-Shastry Hamiltonian. So we can apply the same technique to our result. This is just I'm recalling that we obtained in the previous part of the talk a set of commuting spin operators, and now we're going to use the freezing trick and to obtain the Lagrange spin chain. And this can be done. This can be done by considering expansion of these operators in variable eta. The variable eta is the one which stands in shift operator. So you can consider this decomposition, and D0 here is just a product of functions, and D1 consists of differential part and some matrix part. Some matrix part containing also derivative of R matrices, which is given here. And it can be shown that this D1 part of in the expansion of spin Macdonald-Ruijsenaars operators can be written in the following way, where H tilde are some matrix valid functions which contain R matrix derivatives but doesn't contain any differential operators. And then the statement is if you restrict these H tildes to that equidistant positions or equilibrium positions, then you obtain the commutative set of Hamiltonians for Lagrange spin chain. This statement is non-trivial, and it was proved in our second paper. I also don't go into details of the proof, but I just want to emphasize that this can be done. And here are some examples. Just for shortness, we denote the derivative of our matrix by capital F, and then this is the first Hamiltonian. This is the first Hamiltonian of spin chain, and here our matrices depends on the spectral parameters are fixed as equidistant positions on a circle. So we have the first Hamiltonian in this form, and the second Hamiltonian is the one is given here, and in fact we may compute the Hamiltonians, all high Hamiltonians if you like. And here's just just an example for n equals 3. And it may be verified using both numerical calculations that they indeed compute and prove, and one can prove it straightforwardly. And the proof is also based on some set of elliptic functions identities, which are given here. The E1 function is the first Eisenstein function. It is similar to zeta, the Weierstrass zeta function. It differs from Weierstrass zeta function by linear term. So it's a logarithmic derivative of theta function. And by introducing these two functions, it can be seen, it can be proved that the existence of equilibrium positions in all Hamiltonian flows in elliptic Ruijsenaars model is equivalent to the following set of identities, and it can be verified that these identities are valid, are fulfilled. And so that finally we indeed obtain in an integrable long-range spin chain, and it generalizes the Uglov's q-deformed Haldane-Shastry model to elliptic case on one hand, and on the other hand, it generalizes it to an arbitrary rank, because we don't need only 8-vertex matrix. We may consider any JLM Baxter-Belair matrix and its trigonometric or rational trigonometric degenerations. And finally, I say a few words about non-relativistic limit. And the non-relativistic limit for this chain, so when Q deformation is vanishing, corresponds at the level of our matrices to the classical limit, because H plays the role of relativistic parameter in these chains. And in this way, we the quantum R matrix turns into classical one, and the Hamiltonian, two first Hamiltonians, non-trivial Hamiltonians, are given here. So here is the derivative of classical R matrix, and this is why the models are anisotropic, because in the if we had an isotropic case, then instead of this classical R matrix, we should have some permutation operator multiplied by some function. And such model is also widely known. It is the so-called Inozemtsev elliptic chain. So if you put here the permutation operator multiplied by function, then this corresponds to elliptic Inozemtsev chain. And in our case, we have a kind of anisotropic version for Inozemtsev chain. And previously, this model was found in my joint papers with Ivan Sechin, and at that time we used the so-called R matrix zero flex pairs, but at the time we could just find two first operators, and we didn't know how to prove their commutativity. And now what we obtained the full set of commuting operators. They commute by construction, and if one needs, one can write down all high Hamiltonians as well. And also these models can be considered as a result of application of Prison trick to the model of interacting tops, which I mentioned when talked about kitchen systems on elliptic curve. And so this is the main application of our result. Just to summarize, we described a set of commuting spin operators which generalize Macdonald-Ruijsenaars operators, and then applied the Prison trick and defined elliptic version for q-deformed Haldane-Shastry model. And I may stop here. Thank you very much.
Yes, thank you, Andrey. Thank you very much. Are there any questions? And here is the collaborator. Yeah. So thanks for the. these questions to Andrey. So when you say long range, like all of those, those chains, like every spin interacts with every other, or there's like a
yes. So this is why they're called long range. Just I go back to the definition of Haldane-Shastry Hamiltonian. Yes, usually when talking about chains, we mean that only neighbors interact, but here all spins interact with each other. They're fixed as equidistant points on a circle, but they interact. Everyone interacts with.
And there's no like intermediate regime when you can sort of have, say, k spin, like some number of spins talk to each other, and then not all. Like there's no like there's freezing tricks. Do they allow for kind of intermediate long rangeness? Say 3 spins or 4 spins.
Inozemtsov considered such models. They can be obtained by some limits in procedure, and in fact, you may use, if you put here not the sign but pi function, then and apply a kind of Inozemtsov limit, which shows
so you need to
how
scale some of
the
some anisotropy parameters to infinity, I guess, right? And then coupling to 0. That's okay.
Yes. Then you may even more reproduce the local interaction, like in Heisenberg magnet.
Question. Andrey, there is a correspondence between XYZ model and the 8-vertex model on the two-dimensional lattice. Is there anything like that for these non-local chains and lattice models?
I'm not sure. Maybe not, because this correspondence you are talking about is based on the construction of on the just basic construction of transfer matrix in the scattering method. Yes, and here the construction of a commutative set of Hamiltonians in long range spin chains is very different. It's very much different from the one which is known for ordinary chains obtaining as monodromy matrices and so on. For example, for this Haldane-Shastry spin chain, there is a famous paper by Bernard, Haldane, Godin, and Pasquier, where they found Jungian symmetry of this model, and they conclude that they found the commuting set of Hamiltonians for this model as a center of the underlying Jungian symmetry. But their construction cannot be lifted to elliptic case, or at least this is unknown. So the construction of commuting sets of Hamiltonians in long-range spin chains is different. So this is why I'm not sure about two-dimensional model.
Okay, thank you.
Okay, other questions? Okay, good. So it's time to stop, and thank you very much, Andrey, and all the speakers.
Thank you very much. Thank you very much.
Please don't forget to send me the slides, and I'll see you all at 5 p.m. US Pacific for the continuation for Igor Krichler's talk. Okay, thank you very much, everybody, and see you soon.
Yeah.